What can we say about the expectation and variance of a geometric random variable? Suppose the probability of success is 1/kth. Intuitively, it seems like we should succeed after k trials, and while it's a good idea to build intuition, don't rely on it. So let's see if our intuition is correct. So let's compute our expected value. That's going to be n times the probability that x equals n. We'll substitute in our geometric probability formula, and we can remove a constant factor of p from our summation. To find the sum, note that provided the absolute value of x is less than 1, we can differentiate both sides to get. But note that if n equals 0, we get a 0 multiplier, and so the n equals 0 term of the series can be ignored, allowing us to conclude that, and if x equals 1 minus the probability, the absolute value of x is strictly less than 1, and so we can use this formula uncritically to get. And so our expected value is 1 over p. Summarizing our results, the expected value of a geometric random variable with success probability p is 1/pth, and this confirms our intuition. Next, let's consider the variance. So we want to find the expected value of x squared, which will be n squared times the probabilities. Again, removing a constant factor of p from our summation. And to find the sum, again, note that provided we have convergence, we have. Now, I want to get an n squared, and notice that if I differentiate this, I'll actually get n times n minus 1. But we can fix that. We just need to make this exponent n, and we can do that if we multiply both sides by x. And now we can differentiate, and so we get where our left-hand side is a bit of a mess, but as before, we can let x equal 1 minus p, and that'll simplify to and now we can use the computing formula for the variance. That's the expected value of x squared minus the square of the expected value, and that will be So let's suppose a person pays $100 every year for an insurance policy which will pay $800 upon occurrence of a zombie apocalypse, at which point the policy ends. Assume the probability of a zombie apocalypse can be modeled using a geometric distribution with probability 0.1. Find the expected value of the policy. So remember, concrete doesn't hurt. If the zombie apocalypse occurs after 1 year, then the customer will have paid $100, while the insurance company will pay out $800, giving a payoff of minus $700, viewed from the point of the insurance company because, after all, corporations are all that matter. If the zombie apocalypse occurs after 2 years, then the customer pays $200, while the insurance company pays $800, for a payoff of minus $600. And if the zombie apocalypse occurs after 3 years, then the customer pays $300, while the insurance company pays $800, for a payoff of minus $500. And so it looks like we want to find the sum 100 minus 800 times the probability x equals 1, plus 200 minus 800 times the probability x equals 2, plus 300 minus 800 times the probability x equals 3. In other words, we're looking at 100n minus 800 times the probability that x equals n, or filling in our geometric probability formula. We can split our sum into 2 parts. The second sum is an ordinary geometric series, so we can apply our geometric series summation formula to get and this shouldn't be too surprising since this is just the expected payoff. we can remove our constant factors of 100 and 0.1 from the second sum. And remember that provided conditions that 1 over 1 minus x can be written as the infinite series, we can differentiate both sides to get a factor of n, and substituting our value for x equals 0.9 gives us an expression for the second sum, which we find, and that gives us the expected value of the policy. So again, while we don't want to rely on intuition, it's helpful to build some intuition about probability. Since our expected value of x is 10, then on average we can expect a success, a zombie apocalypse, to occur by the 10th year, at which point the customer will have paid $1,000, while the insurance company will then pay out $800 for a net of $200, which is consistent with the expected value we calculated.